right, so we're going to go ahead and get started. Now, last time we finished up that chapter 2, so we're going to go ahead now and look at some questions from our homework. And we've got one question out of 2-5, and that was question 8. And we probably asked about this one because the slope was undefined. So on question number 8, we wanted to go through this point. So negative 3, positive 5 for the point, and our slope is undefined. Now, this one is not so much calculational. What we're going to be doing on this one is we need to remember our definitions. And so let's take a moment to remember the definition of a zero slope line, what it looks like, and the definition of a undefined slope line and what that looks like. So if my slope is 0, a line that has a slope of 0 would be a horizontal line. So if your slope is 0, it's going to look like this. So this is going to be our line if your slope was 0. And this is going to be a y line. Okay, it crosses the y-axis. So it is a y line. So it's a y-only line. So if our slope was 0, it would be a horizontal line, okay, and it would be y equals whatever your ordered pair would be with the y component. So let's just say this was up 3 units. So this one would be something like y equals 3. Okay, that would be what I'd be looking for. Now, what about if your slope is undefined? Well, it's just the opposite of a 0 slope. So in a 0 slope, that was a horizontal line. So when we talk about an undefined line, okay, undefined slope would mean it would be a vertical line. So let's say it's back here at -5. If your slope is a undefined slope, then that would be a vertical line, and that's going to be an x-only line. Crosses the x-axis. So it is a x-only line. So like, for example, in this case, this one crosses the x-axis at -5, so your answer for that would be -5. Now, what we're going to be doing here on this one is we know we have an undefined slope. Right? And we know that the slope is undefined and it has to go through this ordered pair. Well, when we look at this ordered pair, it's labeled xy. Now, since my slope is undefined, this tells me it's going to be an x line. And we look at our ordered pair, and what's the x component of our ordered pair here? All right, well, our x component of our ordered pair is simply -3. So what would your answer for this one then simply be? X equals -3. And I left that one with answer choices so you could see the difference there. And make sure you notice that on that one, it's an undefined slope. Now, it's not x equals 5 because that will be a y line, right? And ours is x. And what's the x component of our ordered pair? -3. Okay. So did we have any other questions out of 2-5 before we move on to 2, 6, and 7? The only one we've looked at so far was question 8. Give you a moment or two to look through and make sure there's no others before I move on to 6 and 7. And while we're waiting, I'm going to talk about what's going to be happening this week and next week. So this week, we finish up Chapter 2. Last week, we're going to review some of that today, which is what we're doing right now. We do have some extra topics to cover. We've got to cover variation. We've got to cover systems of equations. And we've got to cover logarithms. And those are going to be on our final. So we're going to be covering probably 2 of those topics today. We'll be doing the last one on Wednesday. So whichever one we don't cover today, we'll be covering it on Wednesday. I'm going to go ahead and give you your practice and take-home finals to start working on now. And then Monday, which will be, the 24th, I believe. Okay, so let's just pull the calendar here so we see. So here we are today. Wednesday, we're at the 20th. We're going to finish up everything we needed to cover on Wednesday. We're going to come back Monday. We're going to review. So Monday will be mostly review, just catch up and answer questions, review for your final exam. And then our final will be on the 27th. Now, everything needs to be turned in on the 27th. So anything that you're short and need to complete, it needs to be done and turned in when class starts on Wednesday the 27th. So if you're short homework, if you're missing an exam that you still need to take, make sure all of it is done no later than Wednesday morning. So if you've got exams, you want to make sure you get those done before Wednesday morning. Wednesday morning, what we're going to do is you're going to come in, you're going to take your final. While you're taking your final, I'll be grading your homework, grading your take-home final, so that'll be graded. I should have everything. This is a small enough class. I should have everything graded. And when you finish your final on Wednesday, I'll be able to grade it. I'll be able to put your grading canvas, and I'll tell you what your overall score is right then and there. Because this class is small enough that I can actually keep track of everyone. I'll be able to get everything graded when you're done with your final on July 27th. So make sure that everything is turned in Wednesday morning on the 27th. Okay, so did we find anything out of 2.5 to look at? Any more questions out of 2.5? Okay, well, if not, then we'll go ahead and look at 2.6 and 2.7. Now, 2.5 was mostly a review. You should have seen linear functions and lines from your other courses. Now, 2.6 and 2.7, a lot of it is going to be brand new. And we had some questions. And so what we have out of 2.6 and 2.7 so far was 7, 10, 11, and 12. Are there a few more out of 2.6 and 7 to add to the list? Anything else? No? Okay, then we'll go ahead and finish these. So let's now go ahead and look at some of these. 2, 6, and 7. We combine them together because they're so shorter sections. Question 7. And these are going to be graphing non-linear functions. So we're going to start with question 7. And we want to graph this function. So when we go to graph this function, the very first thing I look at and notice is this is nonlinear. Why is it nonlinear? It's nonlinear because of the absolute value. What does linear mean? Well, linear just means when I graph it, I get a line. Okay, so I get a straight line. This is not going to be a straight line. Why not? Because we have that absolute value. Now I go to the back cover of my textbook, and I look at all the different graphs, and they're identified by the function that relates with them. And I look here and I say, okay, so what is our operation? In our question, the operation is the absolute value. So the absolute value graph makes a V. So our graph is going to look like that. Now, it might be expanded, contracted, flipped upside down, moved all around, but it is going to look something like a V. So my graph at the end will look kind of like this because this is an absolute value. Now, what do we do from there? Well, then we look at our equation and we label. The number on the end, that tells me where I start on the y-axis. So in that case, it's a positive 6, so that means I move up 6 units. The 5 is inside the operation. Now, when they're inside the operation, inside the parentheses, underneath the square roots, those move it left or right. And they're the opposite of the way you think it should go. So just remember that. It's opposite for the left and the right. So in this case, it's a positive 5, so you would think it would move it forward 5 units, but in reality, it's going to do what? It's going to move it back 5 units. So where are we going to now start at? Well, in this case, we're going to start at -5 because we're moving back 5, positive 6. So that's where we're going to be starting at. And then we've got this 1/4 here. And that is not really our slope, but we can kind of use it like our slope. It's kind of an analogy to our slope, because slope is only for lines. But we can use this kind of with our nonlinear functions as well. And we're going to write that as 1/4 over 1. Now remember, with these fractions, you always have to write it as a fraction over 1. If you don't do that, if you write that 1/4, that's going to make your graph look too distorted. So it has to be the fraction over 1. Otherwise, it'll be way too wide, especially with squares and cubes. So that tells me I'm going to go up 1/4 and over 1. So let's now look at our graph. We have to have a V. Where are we going to start at? We're going to start back 5 units and up 6. 2, 3, 4, 5, 6. So that's right about there. Now, what are we going to need to do? Well, we need to make this look like a V, so it needs to look like that. So we take our starting point here. This is, if you study more advanced course, you'll learn this is kind of the vertex of this, the highest and lowest value. And what we're going to do is we're going to go up about 1/4. Now just go up just a little bit and over about 1. So we're going to go up about 1/4 over about 1. And that makes my second dot. Now, what is this graph supposed to look like? When we connect them together, it should look like what? It should look like this V. So we connect the right-hand side first. So there's half of it. Now, how do we get the other side? The opposite. So we start back at our point here. And I know the fractions are kind of difficult to graph, but you just go up just a little bit and over about 1. And that's going to make that second half of the V. And there is your graph. If you're off a little bit in the graph, that's okay. The main thing I'm looking for is to make sure you start at the correct spot and make sure you notice that this is going to be a fairly wide graph. So that 1/4 brings the graph out and makes it wider. If it was like a 7, it would be like that. Okay, it would be very, very narrow. If it was a -7, it would be narrow and it would be flipped upside down. Okay, but ours is right side up because that's positive, and the 1/4 is less than 1, so that's going to expand that graph out a bit. We've got 3 more to look at, and now we're going to move on, and we're going to look at question 10. Now, for question 10, all I want you to tell me is what's happening to this graph. So I'm going to give you this equation. So f of x equals now x minus 8 quantity squared plus 7. And I want you to find the translations. So just kind of tell me what's happening here. So if I was to graph this squaring function, we don't have to graph it, but if we would graph it, it would be a u, wouldn't it? A u that's right side up because it's squared. Now let's talk about the translation. So what's happening here? The 7, where's the 7 at? 7's on the end. So what's that 7 going to do? It's positive, so it forces it up 7. What about the negative 8? It's inside that square. It's negative, opposite of what you think it would do, because you're basically setting it to 0. And that's going to slide that forward to the right 8 units. So what are my translations? I'm going to move the graph up 7 units. And I'm going to move the graph to the right 8 units. So that's what I'm wanting you to tell me. Just tell me the translations. We're not adjusting it at all because there's no number here, so it's assumed to be a 1. So we're not spreading or contracting the graph down. All we are doing is shifting it up 7 units and moving it forward to the right 8 units. The next two that we're going to look at are the greatest integer functions. And these are the only ones that can be a little bit tricky. So we're going to graph now on question 11. F of x equals the greatest integer of x plus 1. Now, what greatest integers do is they round. Right? So they're going to round down. Now, greatest integers is something that we use all the time, and we don't even think about them. So they involve rounding. If I go to the store, I used to go into like Blockbusters, things like that. But those video stores aren't around anymore. But if I go to the store and let's say I rent a tool. Okay, so I've got to rent a tool. And what happens when I rent that tool? So if I go up and let's say I want to till my yard and I rent a tiller. Okay, do I get extra money back if I bring that tiller in early? No, right? But what happens if I bring it in on time? Okay, I paid my bill, right? But what happens if I'm 5 minutes late? If I'm 5 minutes late, they charge you for another day. So what happens is this creates a case of stairs. So when we go to graph these, it looks like a case of stairs. Because you're charged a fixed amount for how many days you rent that tool for. Used to be, I would say, renting DVDs at the store, but we don't rent DVDs anymore. So renting tools, same type of concept. So let's say I go rent a tiller, and I use that tiller, and if I bring that tiller back early that day, I don't get any money back. But if I don't turn it back on time, then I go up to the next level, and I'm charged that full day. And if I don't bring it back that day, I go up to the next level and I'm charged another day, right? So that's why it's a case of stairs. Because bringing it back early is not going to change the amount that I owe. When we go to graph this, it's going to be graphed the same way. Now, what we need to remember is we always start with a closed circle. There's no number on the end. And the number inside is a positive 1. So that's going to slide that graph back 1 unit. So in this case, we're going to have to start at -1, 0. Because we're sliding the graph back 1 unit. And there's no number in front, so we're going to use the 1. So if there's no number here, we should know there's a 1. And that means we're going to go up 1 and over 1. And wherever we start with a closed circle. So we're going to start back 1 unit with a closed circle. And then what we're going to do is we're going to move up 1 and over 1. And we're going to make another dot. So we're going to move up 1 and over 1. Up 1, over 1. Okay, and if I move up 1 and over 1, then that makes that point 0, 1. And that's going to make another closed circle. And then I move up 1 and over 1 again from that point. And if I do that, that makes another closed circle there. And that's going to be up 2, and we went over 1. So that's 1, 2 there. Now, when we go to graph it, we need to make it look like a case of stairs, and the open circles are below. So it's going to look like that. And we can add one more if we want as well. So if we want to add another one, we can go back 1 more, down 1. So that would be 1 more would be at like -2, -1. And you don't need to add very many. Just so you see it, it looks like a case of stairs there. And so what happened to our case of stairs? All we did was we slid it to the right, or sorry, slid it to the left because we went back. We slid it to the left 1 unit. Now, question 12 is very similar. It's another greatest integer, so it'll be another case of stairs. And in this case, we have a 2 out in front. So we know the graph should look something like this again. I always like to do just a quick sketch on the side so we know it looks like that. And that came from the back cover of our textbook. So if you ever need a picture, it's there. Now, where are we going to start at? Do we have any number on the end? Nope. Do we have any number inside the greatest integer bars? No. So we then are going to have to start at 0, 0. So there's nothing on the end, nothing inside. Now that 2 is out in front. And so that means we're going to have that as a 2 over 1. So we're going to go up 2 and over 1. And all that's going to do is make the steps taller, make them steeper. We're not ever shifting it left or right. All we're doing is either making them taller or making them smaller. So we're going to start here at 0, 0 with a closed circle. And now, what are we going to do? We're going to go up 2 over 1 unit. So up 2 over 1, well, that would be at 1, 2. And there's a closed circle there. And we'll do another one up top. So we'll go up 2 units from there, over 1 more. And that would be at about 2, 4. And now we can kind of see, we just draw our lines. You have an open circle below, just like that. And if we want to add another one going in the opposite direction, we can do that as well. We would just go down 2 and back 1. Sorry about that. That's going to be at -1 because we're going back 1, down 2. And it looks like that. Okay. So that's what our graph looks like. Now, what did we do? We didn't move it left or right any. All we did was in having a case of stairs like this tall, we made them steeper. We doubled the height. That's it. So all we did was we doubled the height. Now, if that would have been a half, it would be like that. If that would have been a half in front, they would be half as tall. But in our case, they're twice as tall, so they're going to look like that. And that's it. We never, ever change the left and right part. It always goes over 1. On all of these, we never change the left and right part. When we move to the right, it's always 1. Never a half, never anything else. Always 1 unit over. So that's kind of a basic graph. Now, it doesn't have to be a perfect graph. You've got grids in your homework to kind of help you out, but it doesn't have to be a perfect graph. As long as I can see that you've got the 0, 0 on there, and as long as I can see that you're trying to make it taller. That's all I'm really looking for. Okay, any other questions? 14? Sure. Yep, we can add 14 to the list as well. And on this one, I'm even going to show you why you wouldn't want to make that down 1 over 2. Why you want to make that a half over 1. So I'm going to show you 2 graphs, and I'm going to show you why you want to make sure you make that over 1 here. So let's begin by graphing it the correct way. What should it look like? It's a square, so therefore it looks like a U, right? If you ever need to look at a picture of a graph, go to the back cover of your textbook. You'll find those graphs there. So it looks like a U. Do we have any numbers on the inside? Nope. Do we have any numbers on the end? No. So where are we going to start at? 0, 0. Now this is going to be the correct way of looking at it. When we look at that out in front, that is a minus 1/2. And we're going to have to write that as a minus 1/2 over 1. So this is going to be the correct way of doing it. I'm going to show you the correct way, and then we're going to talk about why, if we did it a different way, your graph would look wrong. And you'll see the difference. So if I was to graph this, I would have to go down 1/2 and over 1. And I'm going to start right here at 0, 0. So because of the fact that that's a negative, instead of it opening up, that U is going to open what? Down. And we're going to go down about 1/2 over about 1. So down about 1/2 over about 1. Make our picture. Or make our line there. And then down about 1/2 over about 1. So it looks like that. And this is the correct way of working it out. Now, this is what a lot of times students do. And this is not correct over here. I am just doing this, and I'm going to put an X through it when I'm done. I am just doing this so that you see why you need to make sure you write this as a fraction over 1. You're going to see that the graph looks different. If I would have used minus 1 over 2, what would have happened to our picture here? We still would start at 0, 0, but look at what would have happened. Down 1 over 2. Down 1 over 2. Do you kind of see the difference between these two? This one is way, way too wide. Okay, notice this one's narrower. It should look like this, not like this. Because when you went down 1 and over 2, it made it too wide. Okay, we don't do it that way. You have to do it as a minus 1/2 over 1. Or what will happen is, especially with smaller fractions, like a third or a fourth even. A fourth would be, you'd see the big difference with the fourth. It would be way, way too spread out. So when you do these, you have to make sure, since it's nonlinear, that you use the fraction. So you have to go down about 1/2 and over about 1. That way it's not too wide. If you go down 1 and over 2, it becomes way too wide. Your graph doesn't look right. So you have to always make sure that if you have a fraction, you write it over 1. Otherwise, you'll end up with some graph that's way too expanded out. And I just want to show you the difference between them. A lot of times I see students make this mistake, and I can tell, because I can definitely tell this is way too wide. And if it was a fourth, it would look even worse. You would definitely see it if it was a minus 1/4 out in front. Any others to look at? Anything else? Okay, well, if not, then we'll go ahead and start the last few sections that we need to kind of cover here. The last couple of topics. We'll pass these out. This will be your last homework packet. I also have your practice final and your take-home final in another packet up here as well. These are going to be our last 3 homework topics that we need to look at. And these are also in our textbooks, so we're going to be referring to those as well. What we have to cover, the last 3 topics, are going to be variation, which I think is important to talk about variation. Oh, did I not give you one? Oh, sorry about that. I just had it here. Sorry about that. Okay, so we're going to talk about variation, which I think variation is really important. We're going to talk about exponentials and logs. And those you'll use if you take a calculus course or statistics. In statistics, we use a lot of logarithms as well, and exponentials. And then systems of equations, which is an easier topic to talk about, but it's something I think we need to discuss too, systems of equations. So those are the 3 topics that we're going to be covering. Now with applications and variations, these are actually pretty easy to set up. And we're going to look at how things relate to each other. And there are different ways that one variable can affect the other. And this is variation, and it's actually in 3.7 in your textbook. But there's different types of variation. Here's one type of variation that we can just talk about and we can understand. What happens when we have inflation? What happens to the prices of food at the store? Goes up. Okay? So as inflation goes up, what happens to the price of food? Goes up, right? As inflation goes down, what happens? Price of food goes down. Variation. One going up affects the other one. Now they can also be inverse, so as one goes up, one goes down. And they can also go by the square or to the power. And you can also have multiple things going together to affect the outcome of something else. Like there could be 2 or 3 things that change to affect the outcome of another one. But I think a good example that we can understand right now is inflation. As inflation rate goes up, prices of goods at the store goes up. That's an example of direct variation. One directly changes the other. Now, when we look at these, there are different types. There's direct variation, which we'll cover first. There is inverse variation, joint variation, and variation to a power. So we're going to first look at direct variation. These are in our textbook, and they're actually in 3.7. And we're going to look at question 27 first. And this is on page 416. And we're going to look at question 27. And this is variation. Now, we didn't cover all of Chapter 3 because Chapter 3, a lot of that is not in our outcomes and objectives. A lot of Chapter 3 is things we don't do anymore by hand. So they're finding zeros, they're graphing complicated functions by hand. We don't really do that so much anymore. A lot of that has been replaced by computers. Finding zeros, a lot of Chapter 3 is just outdated material. We don't do those anymore by hand. So we're not going to cover those, and they're not part of our outcomes and objectives. So we're going to look at question 27, and we're going to see how these relate to each other. And this is talking about the circumference of a circle. So that's the distance around the circle. The circumference of a circle varies directly as the radius. And we know that because as you increase the radius of a circle, what happens to its circumference? It gets bigger, right? The distance around gets bigger. So the bigger the radius, the bigger the distance around. So they directly vary. One increases the other one. A circle with a radius of 7 inches has a circumference of 43.96 inches. Find the circumference of a circle if the radius changes to 11 inches. So this is direct variation, and there is a formula that we use for direct variation. And this formula is actually on page 411, and this is y equals kx, and this is direct variation. And k is your constant. And I picked this problem because we're going to be finding pi. We're going to be finding the constant pi. Another example of a constant might be gravity. All right, so gravity on the Earth is the same everywhere. So that would be a constant. So we're going to try to find that constant. In this case, we're going to be finding the pi. Now, I like to label them with words, so it makes more sense. So it says they vary directly. So a circle with a radius of 7 inches has a circumference of 43.96 inches. So we need to write this as one varying with the other one. So the circumference varies directly as the radius. So the first one we see is the circumference. And that's going to vary with some constant k to the radius. So that's going to be our formula. Now we plug in what we start with, because we're going to be finding the value basically of pi, and this is how they actually came up with pi and figured out what pi was, which is 3.14. It goes on forever. They actually found it by doing variations and recording things. So what do we know about the circumference here? Well, it says the circumference of this circle, to start with, these are starting values. A circle has a radius of 7 and a circumference of 43.96. So 43.96 is the circumference of a circle, Now, k is the unknown. K is the constant that we're going to have to be finding. And what about the radius? This was given in the question, and our radius is 7. Now we can use this to find our value of k. So we just divide both sides by 7, and this finds our value of k. And that's our constant. So 43.96, we're going to divide that by 7, and that gives us 6.28. Now, what is that? Okay, let's take a moment to remember the circumference of a circle. What's the circumference of a circle? Circumference is going to equal 2 pi r, right? What did we find our constant to be? We found our constant to be 6.28. And what is that? Well, pi is 3.14, right, if you round. If you double that, what do you get? 6.28. So we found the value of 2 pi. And we could get 1 pi by dividing by 2. So we found that. That's how they found the value of pi. They looked at circles, they measured them, and they divided out. They found their constant. Now let's rewrite our formula. So when we rewrite our formula, our circumference is going to equal 6.28 times our radius. And now we have to answer the question. So we found our formula. Okay, and this was a basic one. I picked this one because we know what it should be. We know what that k should be. It's 2 pi, right? That's 6.28. So I picked this one so you can see how this is how they actually came up with it thousands of years ago, the value of pi. They did this. They did these exact same calculations. Now, what do we want? We're going to change it. And it says, find the circumference of the circle if the radius changes to 11. So we're going to change that radius to 11. So use your formula. And now we're going to plug in our value. So we're going to plug in the value of that radius, which is 11. And then we just simply calculate it out. So that's 6.28. We're going to times that by 11. And we get 69.08. And that's our new circumference. And that is in terms of, in this case, inches. So that would be your new circumference if we change that radius to 11. Let's do another similar one with direct variation. And we're going to look at question 30, and this one talks about gravity on the moon. So question 30, we're going to be looking at the gravity of the moon. So the weight of an object on the earth is directly proportional to the weight of that same object on the moon. So if you increase your weight on earth, you're going to increase your weight on the moon, right? That's how that works. One makes the other one go up. Now, how they change is based upon a constant. And we need to find that constant. So Earth varies directly proportional to the weight of the same object on the moon. A 200-pound astronaut weighs 32 pounds on the moon. How much would a 50-pound dog weigh on the moon? So the weight of an object on Earth is directly proportional to the weight of the same object on the moon. So Earth is the first one listed. So Earth is, now is means equals. So when we read this, the first one we see is Earth. Is means equals, directly proportional. So that means we have a K involved. I always like to write it out with words so we understand what these pieces mean. So the weight of the object on Earth, is means equals, directly proportional, so that means we have a K here, directly proportional to the weight on the moon. What do we need to do first? Well, it's directly proportional, or direct variation. So our formula is y equals kx. That's direct variation. It just means one influences the other. So the first thing we have to do is we have to find our constant here. The weight of that, okay, so a 200-pound astronaut would weigh 32 pounds on the moon. So what does the astronaut weigh on the Earth? On the Earth, the astronaut weighs the 200 pounds. We don't know our K, we have to find it. And how much does that astronaut weigh on the moon? Well, on the moon, he weighs 32 pounds. So 200 pounds on Earth, 32 pounds on the moon. Let's go ahead and find our K. This one doesn't have any decimals, so we're just going to keep the fraction. So we'll keep the value for K as a fraction. So we're going to divide by 32. And let's see if we can reduce this down a bit. And I think we can. I think we can at least take a 4 out of there. And we'll just keep the fraction. So we'll just divide it by 4. We may have to go further. Because 32 divided by 4 is an 8. And I think we can go a little bit more. And that's going to reduce down finally to then 25 over what? Over 4. So that's our value of K. And you could use a decimal, but we're just going to keep the fraction. Now we can rewrite our formula with our new value for K. That's all you have to do is find the K and then use that to get the other pieces. So now we know our formula for the Earth is going to equal 25 over 4 times the weight on the moon. And that's our new formula. Why is it bigger than 1? Why is 25 over 4? Why is that bigger than 1? Well, what happens on the moon? On the moon you weigh what? Less, right? So if I weigh less on the moon, when I multiply it by its gravitational factor, I get the weight of the Earth. So that's why it's bigger than 1, is because what you weigh on the moon is way less than what you weigh on the Earth, and so you have to multiply it by a factor to bring it up. Now, what are we looking to find here? It says, how much would the dog weigh on the moon? What does the dog weigh on Earth? Well, on Earth, the dog is 150 pounds. Or sorry, 50 pounds, right? So the dog weighs 50 pounds. So what would that be on the moon? Well, plug in my 50. And we don't know our moon weight, so we're just going to leave that as the moon. Now we're missing one variable, so we can quickly solve this. So we'll just multiply it by 4 to clear our fractions. And 4 times 50, well, that's 200. 4's cancel, and that equals 25 times the weight on the moon. We'll divide by your 25. And how much does this dog finally then weigh on the moon? 200 divided by your 25, well, that means the dog weighs 8 pounds. So on the moon, the dog only weighs 8 pounds. He weighs 200 pounds, or sorry, 50 pounds on Earth, but on the moon, that dog only weighs 8 pounds. So all we're doing is finding the constant. And that can be the value of pi, that can be the effects of gravity, some kind of constant, how one relates, it changes the other. That's direct variation. There are some other types that we're going to look at next. And these are going to be either inversely, direct variation to a power. So there's different ways we can look at this, or joint variation. So let's look at some more of these. And let's look now at question 34. We'll do this one, and then we'll take a break. So question 34. So far, we've been looking at direct variation. With these next ones, we're going to be looking at inverse variation. And so that means we make a fraction. So instead of multiplying, the opposite of multiplying is division. So when it says inversely, that means that we have a fraction. We're going to have to make a fraction. Current in a circuit. And this is on page 417. We're looking at the current in a circuit. So the current in a simple circuit varies inversely as the resistance. If the current is 50 amps when the resistance is 10 ohms, find the current if the resistance is 5 ohms. We need to make sure that we set these up correctly. The current in a simple electrical circuit varies inversely. So we've got current going first, so that's going to be our first thing, varies inversely to the resistance. Now, inversely means we have a fraction. So when we talk about inverse variation, this is what it looks like. And it could even be inverse to a power, which we'll talk about powers after break here. But we're going to do this one. We'll take a short break, then we'll come back and we'll do more of these variation problems. So inverse variation just means we make a fraction. And we always look at which one is listed first. And that's how we set these up. And this, by the way, is on page 417. And we are going to look at question 34. And it says current, so that's what we start with, varies inversely. Okay, so current varies inversely, so that means we have to divide. So pick up on those keywords like inverse. It varies inversely to the resistance. So that's going to be our new formula because this is inverse variation. And it's easy to remember whenever we have inverse variation, we just make a fraction. And we could use x's and y's, but students get confused with those. It's better just to label them so we know what we're looking at and not get confused with the x and y, because then we don't know which one is which. So I always like to just use the words. Now, when we read this, it says inverse is resistance. If the current is 50 amps, resistance is 50 ohms. So we're going to, or 10 ohms. So we're going to go ahead and fill these in. So my current from the question is 50. K again is the unknown part here. And what's my resistance? My resistance is 10. So we filled it in. The current went in, resistance went in. Now, we can find our value of K. So now we're going to solve this for K. So how do we solve this for K? Very simply, we just do what? Cross multiply. And so 50 times 10, that makes it 500. So that's our value of K. That's all we have to do. Now, once we have found our value of K, then we can rewrite. So now our current is going to equal now 500 over the resistance. That's our new formula. Plug in our value, and it says find the current if the resistance is 5 ohms. So the resistance now is going to be 5 ohms, so we plug it in. Right, so when we do that, 500, we divide that by 5, and that gives us then a current of 100 amps. So that's what happens with inverse. When inverse, it's the opposite. So when one goes up, it forces the other one down. So in this case, as we decrease our resistance, our current goes up. Just so you know a little bit about what current and what resistance is, think about wires. All right, so if we want to have a higher current in our home, or some appliance that draws a higher current, it has to have a thicker wire. Because resistance, the bigger the wire, the smaller the resistance. So that's why things like your oven or anything that requires 220, those have thicker wires in some cases because we have to have more current. And how do we get that? Well, we decrease our resistance. Because resistance is just basically the flow of electricity, how easy it is to flow through electricity, through wires. And the bigger the wire, the easier it is. So that's why we increase the size of the wire so we can have more current. But that's how they relate. So as you decrease the resistance, bigger wire, you can hold more current on that circuit. Let's now go ahead and take a short break. We'll come back and we'll look at some more variation questions. So let's meet back here in about 10 minutes.